Good evening, everybody. It's a Sunday evening where I live. It's been a rainy day, and I am struggling from being really tired because it has been daylight savings time today, and I lost an hour of sleep last night. So, has nothing to do with soil mechanics, but hey, that's just me. So I thought I'd share a little bit of that with you, as well as the two topics that we're going to discuss in today's lesson. These two topics are different and yet related, and so I combine them into the same lesson. And both of them are important, especially when we deal with slope stability assessment or the looking at the factor of safety against a slope failure. So let's talk first about clay sensitivity and quick clays, and then we'll move into anisotropy and why that is significant when we deal with shear strength in clays and in silts. So clay sensitivity, let's get a couple definitions down first. So first, if we talk about a sensitive soil is any soil that's going to lose substantial strength when we disturb it or when we strain it, when we remold it. In other words, if we apply any sort of strain or deformation into that soil fabric, it's going to soften and lose its strength considerably. Now, the other definition is quick soil. So a quick soil is a sensitive soil that is particularly sensitive. So a quick soil isn't just going to lose a substantial portion of its strength. A quick soil is going to lose almost all of its strength. And so when we evaluate soil sensitivity, we're going to calculate it as S sub T, and it's a simple calculation. It's just a ratio. It's the ratio of the undisturbed, pardon that typo, the undisturbed undrained shear strength of the soil versus its divided by its disturbed undrained shear strength. Another way to think of this might be as the peak divided by the residual undrained shear strength. This is just another way to think of it. So if we were to develop a scale of sensitivities, then these values right here might apply. This is at least a set of values that are common here in the United States. So if I have, for instance, a sensitivity of 1 to 2, we'd say the soil is not really sensitive. 2 to 4, the soil is medium sensitive, sort of sensitive. 4 to 8, we'd say the soil is highly sensitive here in the United States. I know that in other parts of the world, that definition may not apply, but here in the United States, it does. And then if we get into sensitivities ranging from about 8 to 16, this is where we start to say, okay, we're getting into the quick range now. So we have slightly quick, 16 to 32, medium quick, and anything larger than 32, we have very quick soils. Now in Scandinavia, they have some quick soils that have sensitivities greater than 50 and some even approaching 100. And so those can be very, very dangerous soils to build upon, and they need to be engineered by those that are familiar and experienced with those types of soils. If you guys want to see some cool stuff, check out this address here. This will just is a clip from the quick clays in Norway. It's from the Norwegian Geotechnical Institute. It's just a clip from a very old video about the Rissa landslide. But they do a nice little experiment and a demonstration that shows off what quick clays are, and it's pretty mind-blowing. So let's talk a little bit about how quick clays are formed. So in these environments, usually during deposition, the ocean is at a higher level, and the land is beneath the ocean. And so we might have rivers coming into the ocean, and they're depositing all sorts of sediment that they've picked up in their erosion, and that sediment gets deposited on these marine terraces. Now, for geologic reasons, climate change, geostatic uplift occurs, or the ocean levels drop. Those have happened many times over the history of the Earth. And as those ocean levels drop, or the land rises due to geostatic uplift, that exposes this marine terrace to the atmosphere and to fresh water. So as it rains or as rivers begin to flow over that marine terrace, that fresh water will leach down through this marine terrace, which was formed, by the way, with lots of it was formed with sediments in the presence of sodium with ocean water. And so when the sodium cations go into that formation of that sediment, it causes a higher valence and a thinner double layer. So if we have a higher valence and a thinner double layer, then we have a flocculated structure in that soil when it's deposited. But as that sea level drops, that fresh water leaches out that sodium. Then once that sodium is leached out, the clay doesn't want to have a thin double layer anymore. It wants to have a thick double layer. And with a thick double layer, that corresponds to a dispersive depositional environment. So this is the danger, because now we have a soil that is in a flocculated state, but the soil wants to be in a dispersive state. So the soil now becomes what we call metastable, meaning it's in a flocculated state, but it doesn't want to be. And any sort of disturbance, any sort of strain, any sort of jiggling or wiggling or extra shear stress can cause the soil to collapse and immediately and rapidly form a dispersive molecular structure. And that is the soil, in essence, turning to, right before your eyes, turning into a fluid. So how do we identify a sensitive or a quick clay? There's a couple tricks that a geotechnical engineer can use. One of the easiest tricks is to look at the liquidity index. The liquidity index is calculated from Atterberg limits and the moisture content of the soil. So here's the equation for the liquidity index, where this W is the natural moisture content of the soil, PL is the plastic limit, and LL is the liquid limit. So the liquidity index is very easy to compute, and here's how it relates to sensitivity. If the liquidity index is around 1 or greater than 1, then the soil likely has some degree of sensitivity. If the liquidity index is well above or much greater than 1, then it probably is sensitive. Now, if the liquidity index is less than 1, that implies that the soil is more likely to be overconsolidated. And so overconsolidated soils are not, or they tend not to be sensitive. So that's the first thing we can do. The second thing we can do is just test the soil in a laboratory. So we obtain relatively undisturbed soil samples, the best that we can from the field. We bring them to the lab and we test them in a triaxial device or a direct simple shear device, and we try to compare the peak undrained shear strength against the residual undrained shear strength, and we compute the sensitivity of that soil. And so that's a reliable way. That the challenge here is getting undisturbed soil specimens into the lab. And third, we kind of know where these soils are located just through history and through our understanding of geology and geomorphology. Most quick clays are located in Scandinavia, Norway, Sweden, and Finland, and also a similar depositional environment in eastern Canada. Now, sensitive clays, so they don't have the sensitivity as high as quick clays, but they're still sensitive. They tend to occur in normally consolidated clays. So anywhere where we have normally consolidated clays, particularly clays from lacustrine deposits. So lacustrine deposits are deposits of clays or silts in still or slow-moving bodies of water. So this might be like San Francisco Bay. So San Francisco Bay is famous, or maybe I should say infamous, for bay mud. It's some pretty nasty, gooey stuff. Salt Lake City has the Bonneville clay. It's not terribly sensitive, but there are places, especially if it gets some fine sand particles in it, it can behave sensitive. And also another place that has sensitive clays are portions of Mexico City Basin. Lake Texcoco, I think that's how you say it. Yeah, my friends from Mexico are going to make fun of me for slaughtering that. But anyway, an ancient lake that used to be there, Lake Texcoco, yeah, it had some very, very soft sediments. And those soil sediments are very, very sensitive and weak. Okay, let's switch gears now, and we're going to talk about anisotropy. So anisotropy, at least in the sense that we're going to talk about it right now, is the difference in shear strength from horizontal to vertical. So oftentimes we like to assume that soil is isotropic, meaning that it has the same strength horizontally as it does vertically, but we know that this is not true. Soils are anisotropic, and so they have variable strength depending on the orientation of the failure plane and also the orientation of the axis of loading. So let's try to understand where this anisotropy comes from. So the first source of anisotropy comes from the way the soil itself was deposited. So typically soil is deposited in horizontal beds, just like this. And all the weight of the soil is straight vertical up and down because that's the direction of gravity. If I could learn to spell, there we go. So soils that have plate-like or platey particles, they are going to deposit themselves in sheets. They're going to orient themselves perpendicular to the major principal stress, which in this instance is in the vertical direction. So a couple of examples of this type of behavior would be maybe a shale or a mudstone. So oftentimes when we see shale, we see depositions that look like this, where we have a strong shale layer and then a weak layer, and then a strong layer and then a weak layer, and it just you can see right here, strong, weak, strong. There's a little weak one right there. The point being that this clay, when it was deposited seasonally, or it could be indicative of cyclic changes in climate that led to that. But the point is that you have this kind of sandwich of strong and weak layers. And so in soils like shale, you have layers that tend to attract load and tend to have failures in them. So that's something to be aware of. Similar to shale or mudstone, we have varved clay. Now this isn't stone, it's actual soil, but varved clay occurs in lacustrine environments where due to seasonal changes in deposition, from clay to silt to sand, back to clay to silt to sand, we get all these beautiful layers that, I mean, it's really pretty to look at, but it's a pain to deal with as an engineer because those layers have different soil properties. Some layers are weak and some layers are strong. So we have to account for that. A second cause is the orientation of the principal stresses and the failure plane. So here we have two examples, right? We have, in this instance, let's pretend that the vertical is the larger and the horizontal is the lesser. And so we have axial compression going on. And in axial compression, we've learned from studying Moore's circles and the origin of planes that the failure plane for axial compression is going to be oriented at an angle of 45 degrees plus phi over 2. And that's drained, by the way. We should point that this is all drained loading here. We're not talking about undrained yet, okay? Now, we also could see an instance where maybe the horizontal stresses are the largest and the vertical stresses are the smallest. In this instance, it could occur either because the horizontal stresses stay constant and don't change, and the vertical stresses unload, hence you see these arrows going upwards. Or it could be due to the horizontal stresses increasing and the vertical stresses staying the same. Either way, we still get axial extension. And so the failure plane for that is an angle of 45 degrees minus phi over 2. Now, whichever one of these shears, either compression or extension, is greater is influenced by the reversals of the stress. So let's look what we mean by that. Here we go. We have a figure here of some Moore circles. And we have an initial Moore circle here and isotropically consolidated. Sigma 3 stays the same. So this would be, again, sigma 1, sigma 3, and then the deviator stress. So this is axial compression, okay? So sigma 3 is not changing, it's staying constant. There we go. Okay, so as sigma 1 grows due to the application of the deviator stress, those Moore circles get bigger, our stress path goes up and to the right, which is indicative of axial compression. In this case here, we have examples of axial extension where maybe for this example, sigma 3, this is our initial circle, but we increase sigma 3. So this time, we're applying a deviator stress in the horizontal direction. So now sigma 3, the horizontal, gets bigger and starts to move to the right. And it gets, so our circle gets smaller and smaller, 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 until eventually the horizontal stresses become larger than the vertical stresses. And so now our circles start to get bigger and bigger, where sigma 1 is now in the horizontal direction and sigma 3 is now in the vertical direction. So that would be a case of axial extension. Now, if we were to look at Skempton's pore pressure relationship, and remember that the A parameter deals with the change in pore pressure from shearing, and this change in sigma 1 minus the change in sigma 3, this is just the diameter of our Moore circle, so that's the deviator stress. So since we have that relationship, and since we know that the change in stress in the extension is greater than the change in stress in compression. How do I know that? Well, look at this distance compared with this distance. This one is greater. Since we know those two things, then we can make a couple of statements. We observe generally that if we have normally consolidated soil, meaning that A bar is a positive A is a positive number when we shear it, then under drained conditions, the shear stress in extension is going to be less than the shear stress in compression. But if we have an over-consolidated soil and the A parameter is negative, then it changes and it reverses. In this instance, the shear stress in extension is larger than the shear stress in compression. So in other words, for an over-consolidated soil, this shear strength from extension is going to be larger than this shear strength from compression. And that's an interesting phenomenon. It may not make sense, but let's try to dive in and understand why. Let's consider a couple of things. First, let's go back to my whiteboard and let's do a little sketch here to help you guys understand. You have to remember that we have to think about these things in 3 dimensions now. So I'm going to draw a cube of soil. And this cube of soil has stresses acting on its 6 axes. Okay? So whichever axis has the largest stress, maybe let's do axial compression. We would say in axial compression, the vertical stress is the largest, so we'd assign that as sigma 1. And then we'd assume that the 2 horizontal stresses are approximately equal. And so in this case, for axial compression, we're going to say that sigma 2 is going to equal sigma 3, okay? But what about the case of axial extension? Now, in this case, we're going to say that the horizontal stress is going to be the largest of the stress. But we're also going to say that this horizontal stress is going to, sigma 2 is going to have the same stress, and the vertical stress is going to be the lowest. So in this instance, for axial extension, we're going to say that sigma 1 is equal to sigma 2. For this case, in this case, the horizontal stresses are larger than the vertical stresses. So that's indicated mathematically here. So for triaxial compression or axial compression, the vertical stress is the major principal stress, and the horizontal stresses we're going to call sigma 2 and sigma 3. And remember, all these have primes next to it because, again, we're talking about drained loading. Now, in triaxial extension, or the same as axial extension, the vertical stress is the smaller of the stress. And the horizontal stresses, we're going to say they're equal, and we'll call them sigma 1 and sigma 2 because they're the major principal stresses. So in this instance, the vertical stress is less than the horizontal stress. So for the case of triaxial compression, one axis, the vertical axis, has the big stress. And 2 of the axes on our cube have smaller stresses. For axial extension, 2 of the axes have the big stress, and 1 axis, the vertical one, has the smaller stress. So if we were to compute the mean stress from all of these, if we were to compute those, what we would find is that because in axial extension, 2 axes have the big stress and only 1 has the small stress, the mean stress, the mean effective stress in triaxial extension is typically larger than it is in triaxial compression. And because the mean stress is larger, it also has larger apparent strength. Remember, shear strength of soil is a function of its confinement. And the larger the mean stress, the larger the apparent shear strength. Hence, for drained soils, the friction angle in triaxial extension is usually larger than the friction angle is in triaxial compression, usually between 5 to up to 25%. Check this out. Here's some charts that engineers can use today to try to predict the different friction angles for compression and extension. Now, the way this works is on the x-axis down here, we have this term called B. And all B is the difference between sigma 2 and sigma 3 divided by sigma 1 and sigma 3. So in the case of axial extension, sigma 2 and sigma 2 is equal to sigma 1. So this would be the same as sigma 1 minus sigma 3. And so if that's the case for axial extension, then this ratio would just equal 1. Hence, you see axial extension for a B value of 1. Now, in the case of axial compression, sigma 2 equals sigma 3. So we can substitute sigma 3 in for sigma 2, and that's just going to equal 0 for axial compression. So that's why the B value corresponds to axial compression. And for everything in between axial compression and axial extension, we have all of these other things, okay? And this ratio right here is the ratio of the friction angle of axial compression divided by the friction angle, the friction angle of whichever B we're at, divided by the friction angle of axial compression, or a B equals 0 condition, okay? So that makes sense, because at B equals 0, that ratio should be equal to 1. So notice how everything normalizes to a value of 1 at B equals 0. But check this out. For most soils, once you move away from axial compression and start moving towards extension, those friction angles go up. They go up, up, up. And so now we're in ratios anywhere between about 25% higher to about 5% higher. So this is where that 1.05 to maybe that looks like about 1.23 or so within that range. So that's where that 5% to 25% comes from. And all of that is because as you move towards axial extension, you have a larger mean stress in your soil. Here's another plot from Coolhowie in Maine that shows the friction angle from triaxial extension versus the friction angle from triaxial compression. Now, if these were equal to one another, what you'd see is this dashed line, meaning a one-to-one relationship. But all the data plots above that line, meaning that triaxial extension tends to have a larger friction angle than triaxial compression. How much larger? Well, the mean curve of that is given by this relationship here, where on average with the data they plotted, it was about 22% higher for triaxial extension. And again, I know I've said it before, but I want to make sure it's crystal clear. All these plots I'm showing are assuming drained loading. Okay, we're talking about friction angles here, so it's drained. But what happens if we have undrained loading? And we don't want to assume that the soil has a friction angle. Instead, we want to use an undrained shear strength. Well, things change quickly in undrained, and everything that I just talked to you goes out the window. With undrained loading, the effect of the mean stress in that sigma 2 is much less pronounced, and instead, the anisotropy of the soil fabric governs. So here's what we tend to see. In undrained conditions, the extensional undrained shear strength is less than the direct simple shear undrained shear strength, which is less than the triaxial compression or axial compression undrained shear strength. Here's a nice plot I believe this was developed by Chuck Ladd, I believe. I don't have a reference on here, but I believe this comes out of his work with Shansett. And what he's showing here is ratios of undrained shear strength divided by initial vertical compressive stress, or vertical effective stress. Okay, so this is just the ratio. And what we tend to see is that triaxial compression has the highest ratios. We're hovering right around the 0.32 to 0.33 range for that ratio. Direct simple shear, check this out. This line ranges from about 0.22 all the way up to about 0.25 or 0.26. Triaxial extension, on the other hand, we're down to as low as around 0.15, and we get up to maybe 0.23 or so for that ratio. So for undrained conditions, it's much different than it is for drained conditions. Now, it's important to note that this figure right here and this relationship is true for normally consolidated clays, but it's not necessarily true for over-consolidated clays. Well, why? I'll show you in 1 minute. But first, to show you this figure I want to show you, let's get a little bit of vernacular down. And let's look at just a schematic of a failure plane and a slope. Now, you can see that the soil is deposited in horizontal layers. And next to each of these conditions, you see a number, an angle labeled beta. And this angle beta is the angle between the applied load on the soil and the angle of the bedding plane. So in other words, here's the angle of the bedding plane. Here's the angle of the applied load. So that angle between them in this case would be 90 degrees. That's why beta is 90. Down here for direct simple shear, there's the angle of the bedding plane. Here's the angle of the loading. So that angle right there would be 30 degrees. So that's why beta is 30 degrees. There was a typo in this figure. We corrected it. It's supposed to be 0 degrees because here is the bedding plane and here is the angle of loading. So the angle difference between those two is 0. And hence we have a beta of 0. So in this instance up here where beta is 90 degrees, that is axial compression. Down where beta is equal to 0, that corresponds to extension, axial extension. And in the middle right here, this is going to correspond to direct simple shear. Okay. So now that we have that vernacular down, let's have a look at this plot. Good stuff here, okay? So for what we have on the y-axis here is we have a ratio. We have the ratio of the undrained shear strength of your soil divided by the undrained shear strength for the vertical loading, or the case where beta equals 90, so axial compression, okay? Now down on the x-axis, we have, for whatever soil you're testing or loading, the angle beta, the angle between the loading and the angle of deposition of the soil. So at beta equals 90, we would expect then this ratio to be equal to 1, which you see everything gets normalized at 1 right there. Okay, so right here at 45, this is direct simple shear, and at a beta equals 0, that's triaxial extension. Just so you're aware, okay? Now, let's have a look at these different soil types that are here. This is just a small example of the soils that we have. These first two right here, this bear paw shell and this pepper shell. Shell is heavily over-consolidated, folks, so it is very stiff, heavily over-consolidated. And then we have a couple soils here. called Atchafalaya clay or San Francisco Bay mud. These soils are normally consolidated and they're very soft. And then we added our own from Utah, from Lake Bonneville clay. We just drew that in here ourselves. So let's have a look and see what behavior we can see. For the normally consolidated soils, they follow this trend generally that looks something like this, where for axial compression, we tend to see the larger shear strengths as opposed to axial extension, okay? And direct simple shear is kind of in the middle. Now for over-consolidated soils, the anisotropy looks something like this, where the largest strengths come from axial extension due to dilation in the soil. The second largest strengths tend to come from axial compression, and the weakest state of the soil is in direct simple shear. And that, my friends, is because of the planes of weakness that are already in the soil. And so what lessons then do we learn? For soft, normally consolidated clays, we see this relationship holds true, that the triaxial extension shear, undrained shear strength is less than the direct simple shear undrained shear strength, which is less than the triaxial compression undrained shear strength. But for stiff over-consolidated clays, especially those that have varves, fissures, or preferred planes of weakness in them, the trend tends to be like this. The undrained shear strength from direct simple shear is the lowest, followed by the undrained shear strength from triaxial compression, followed by the undrained shear strength for triaxial extension, which tends to be the largest. So why is this important? Well, if you're doing a slope stability analysis and you have your slope that looks like this, and your computer develops a failure plane that goes like this, and the computer program is going to assume that the soil is all deposited like this. So it's going to look at the failure plane coming in, and it's going to say that's beta equals 90 degrees, hence that's triaxial compression. And down here at the bottom, when that failure plane's coming in at 30 degrees, the computer is going to say that's direct simple shear. And at this instance where the failure, the maximum principal stress or the load is hitting the soil right at an angle of the deposition, so beta equals 0 degrees, hence the computer is going to call that triax extension. It needs to know what shear strengths to apply here, here, and here. If you don't tell it that, it's going to assume isotropic conditions, where it's just going to apply the same shear strength. Whoops, don't want to lose my... It's going to apply the same shear strength to the entire shear surface. And that is not accurate, because soil behaves anisotropically. So if you want to capture those effects in your slope stability analysis, then you have to, your software is typically going to ask you to input these types of ratios. It will ask you and say, hey, give me these values, give me these ratios, and I'll go ahead and account for anisotropy. Some of the more modern software has some default anisotropic ratios built into them, but not all of them do. And if you don't account for anisotropy, then the program is going to assume that you want isotropic conditions. Another thing that we have to consider when we deal with soil anisotropy is the amount of strain required to develop the various peak shear resistances. So this figure here was shown from Chuck Ladd. So let's assume we have a soil and we load it up in compression, and it'll load up under compression, and it will peak under a very small strain, maybe just 2%. And then it starts to drop and lose shear resistance immediately. Now say we were to load up another soil specimen in direct simple shear, and it might do something like this. It won't peak until somewhere between 8 to 12% strain. So at 2%, where the triax compression peaked, we have not reached peak shear strength in direct simple shear yet. And for triaxial extension, it requires a lot of strain until we hit our peak. Look at that, 16% strain until we finally reach our peak shear strength of that soil. And so what does that mean? Well, what it means is that, again, if I draw my little slope failure, where I have triax compression, direct simple shear, and triaxial extension, what it means is that my soil right there is peaking in its shear strength before my soil at the bottom does, and especially before the soil at the toe does. And if we make the mistake to assume that I have peak strengths occurring at the same time in my analysis, I can get myself into trouble, because what can happen in the field is what's called a progressive failure. Sometimes some engineers call it a zipper failure, where we get failure at one point of the slope, which leads to failure in the next part, which leads to failure in the next part, which leads to failure in the next part. And so it's this progressive failure till finally the whole slope just goes. That's what we call a progressive failure. So this figure from Duncan and Wright is a really good demonstration of it. Now imagine we have 3 points, A, B, and C, along the bottom surface of this slope, okay? And the slope is experiencing rebound, so it's wanting to strain and come out. So say we made an excavation. Okay, so as the soil begins to strain and experience displacement, point A right there is going to peak before point B does, because it's going to rebound near the ground surface before it rebounds at point B. So by the time then that B reaches its peak, A is already past the peak and has less strength, and C hasn't reached the peak yet. By the time the strain reaches C and C peaks, both points A and B are already softening and are losing strength. So at no point in this process did we see peak strengths at A, B, and C at the same time. So if an engineer assumed peak strengths occurring at the same time at points A, B, or C, you might end up with a failed soil slope. So what do engineers do to overcome this? Well, a couple things. Maybe they'll assume an average strength. So maybe they'll kind of cap a strength right there, and they'll say, okay, this strength right there, that's the strength we're going to use for design. So it's something less than the peak strength. And it represents something more of an average strength so that we can ensure strain compatibility. That's one thing we can do. Another thing that we could do is that we can go ahead and just design to maybe the residual strength at a large strain. So a softened, or even in severe cases, the residual shear strength. And that way we can cover ourselves in the event that large strains occur or even a slicken side develops. Now bear in mind that if you use residual shear strengths, that you're going to have much lower factors of safety in your soil slope than you would if you use peak shear strengths. But it can be dangerous to use peak shear strengths because the peak shear strengths just may not be there in the field. So that's the end of our lesson today. I hope that what we learned today in anisotropy and also talking about clay sensitivity was useful to you. Feel free to leave any comments with questions. If I get a chance, I'll go ahead and respond to those for my students. If you have any questions, shoot me an email or come see me when I return from my trip. I'll be happy to discuss your questions with you. Hope you have a great day, and I will talk to you later.